Hi, in today's video we'll talk about a sensor that is very simple to use. A sensor might have a lot of applications, for example, warn you against thieves in time who would secretly want to steal your valuable collection of post stamps, or, for example, illuminate the room when you are unable to find a switch, and most importantly, it's very cheap. At the end, I'll show you how to use it to make a simple LED strip switch that you can hang, for example, in the corridor or nicely decorate the passage. I present a hero of our today's video, the HCSR501 motion sensor. Please enjoy the video. As has been said before, it is a motion sensor. This means that it can detect move that occurrence, and this occurrence is signalized digitally by a high status. Firstly, let's say something about the basic parameters. This model can be powered from a very wide range from 5 up to 20 volts, and what's important, this voltage is stabilized at 3.3 volts thanks to the 71331 stabilizer. Current consumption during motion detection is about 65 milliamperes, and during standby it is less than 50 microamperes. The model works in TTL logic, while low state is of course 0 volts, and high is 3.3 volts. The datasheet also indicates that the measurement can be made up to 7 meters, and the angle of view of the sensor is up to 120 degrees. Although after tests, in my opinion, it's more than specified by the manufacturer in datasheet. Okay, that's all when it comes to dry facts. Let's move on to a more detailed description. These sensors, and also of course this one, consist of two main parts. First of them, you can see it over here in the middle of the screen. Yeah, is a pyroelectric sensor element. And the second element, also you can see it, is a so-called Fresnel lens. Pyroelectric is a material that has the ability to generate electromotive force under the influence of temperature changes. And the second part, the Fresnel lens, is an optical element consisting of many optical lenses. Wait a moment, as you can see. So yeah, here you are, the first one, second one, third one, fourth one, and so on. Their specific construction allows to focus, the radiation comes from different ways at the one point. Also, the phenomenon called the spherical aberration is very low here, and I think that's especially those who are fascinated with astronomy. I don't have to convince that this phenomenon is very undesirable for us astro amateurs. But let's stay focused on our main topic. Yeah, what's important? The pyroelectric detector, this one placed in the middle of circuit board, can also detect infrared radiation. And as I suppose, all of you or most of you know that all objects above absolute zero temperature, so 0 Kelvin or minus 273.15, as I could remember, Celsius degrees, emit infrared radiation, including human bodies. The pyroelectric sensor has two rectangular slots made of material which let infrared radiation pass through them. Behind slots are two separate electrodes of infrared sensor, one responsible for producing a positive output signal, and the second one for a negative output signal. When the sensor is idle, when there's no movement around the sensor, both electrodes detect the same amount of infrared radiation, resulting in a zero output signal. But when there's a movement of a body nearby, and what's important, when I say body, I mean not only the human body, I mean also, everything all around us. So, body can be, I don't know, even door or a chair. You know what I mean. So, if there's a movement of such body nearby, which, as we know, if its temperature is not absolute zero, it emits infrared radiation, and this radiation is detected by the first half of PIR sensor, which causes, as I said previously, positive signal, and in this case also difference between two halves. And then when the warm body leaves the area of the first half and enters the area of the second, the sensor generates a negative signal, and an appropriate pulse signal causes the output to be set to high. I think this is a very good solution because we do not rely only on a temperature gradient. Let's imagine the situation that we suddenly turn on the radiator based on infrared radiation, which instead of generating heat by convection, as we know it from classic radiators, infrared radiator hits us with, as you can suspect, infrared radiation. The farther away from such radiator, the higher temperature changes the sensor can see. But what's important, no movement occurs here. This solution, with gaps and so on, allows to prevent such undesirable situations. Okay, so now when we know the principle of detector, let's describe the detector and tell something more about things the detector has been equipped with. We can find two potentiometers here and here, and here in a right corner, in this case, trigger selection jumper. This is the yellow one. You have 3 pins over here, and that allows to set single or repeatable triggers. I'll explain it later. So yeah, there's no much to talk about in this matter, so let's start. Okay, the first potentiometer, so the left one, uh, is is responsible for sensitivity. It set the maximum distance the motion can be detected, and in datasheet, sorry, and in datasheet is written that the distance is up to 7 meters. The second potentiometer, so this one, uh, determines how long the output will remain high after detection. According datasheet, a minimum period is it was something about 0.3 second and maximum up 5 minutes. After this time, there's also so-called by me that period in which no detection can be made. In addition, we have trigger selection jumper, previously mentioned by me, and it defines how the sensor reacts to motion. We have two configurations: low state L. Maybe you will be able. Oh yeah, here's the letter L. Wait a moment. Okay. And the second, but it's no written over here. No, I don't see. And the second option, high state. Yeah, but as I said, it's no written. Yeah, and this signal is then sent to the BISS0001 chip. This is the one. Yeah, which I will talk about in a moment. Speaking the simplest language, in the case of the low state here in the trigger, the sensor, if it detects movement, set high state to the pin which informs about this fact and becomes insensitive to other movements if they occur. Then it counts down the time that was given to him through the previously mentioned one of the potentiometers. And after time goes by, a low state is set on the sensor output. Sorry, if this trigger, if this jumper is in the high position, the sensor, when it detects motion, will start counting down the time during which the output pin will be in a high state. However, there's the difference. If another movement occurs during the high state and the sensor detects it, then the time during which the output is in a high state is counted again from the beginning. So hypothetically, yeah, I think it's good pronunciation, sorry. So hypothetically, if motion detection repeats often enough, the output will be in a high state all the time. Okay, slowly approaching up to the practical part and presentation the project that we will build today. It's worth to mention about small chip that manage all of this. Previously mentioned chip BISS0001. This chip is made in CMOS technology, is very resistant to noise and interference, and can operate in earlier mentioned two modes. the so-called retrievable and non-retrievable modes. Which are used in the already mentioned method of counting time after motion detection. It has a low current carrying capacity, only 10 milliamperes, so be careful. And the supply voltage ranges for this chip, of course, is from 3 up to 5 volts. I also have something for those who are the bravest DIYers. If you only belong to this group, you can set your own duration time of the high state, and as I mentioned earlier, the so-called dead time. As you can see in the diagram presented on the screen now, the duration time of the high state is the product of two variables and one constant. The number 24576 and the value of resistor R10 and the capacitor C6. Is something wrong with this sentence? If no, then it should be. And I'll explain why. The resistor value is constant and normally is unchangeable. So how it's possible that we can use the potentiometer to regulate the time of high state output? The answer is very simple. The resistor shown in the diagram as R10 and the potentiometer used to adjust the duration time of the pulse are connected in series, which allows you to adjust the duration of the high state. And the duration of the dead time is the product of the number 24 and the value of resistor R9 and the capacitor C7. Okay, and I'll show you very fast on the circuit board the resistor and capacitors. Okay, and I'll show you very fast on the circuit board those resistors and capacitors. Okay, wait a moment, please. Okay, so this capacitor and the resistor that is below the capacitor are responsible for that period time, and this resistor and being next this capacitor are responsible for time of high state on the output. I think that's all when it comes to theory. And let's move to something more interesting. Let's move to practical things. Hello once again after a short break. As mentioned in the video title, today we will make a lightning using a LED strip and switching it on using a motion detector. It is a very simple project and that can be used, for example, for corridor lighting. Of course, it's possible to modify it, for example, by adding a photoresistor, which instruct the microcontroller whether it's already dark enough for the motion sensor to come into action, or a button that completely turns off the sensor and allows you to control the LED manually. Okay, but first I'll show you quickly how to connect a single diode with and without a microcontroller, and of course using our motion sensor. The code for Atmega 8 is so trivial that I won't make a separate chapter here for its writing and describe it. everything you need you can find in the description of the film. So without extending, let's go to work. Project is trivial, as you can see. It consists of an Atmega 8 microcontroller, resistor, LED diode connected to the one of the one of the pin of a microcontroller declared as output, and of course our sensor. It doesn't require any additional resistors, plus to plus, minus up to minus, to the ground, and the output pin, of course, also up to one of the microcontroller's pin. Of course, we have traditionally over here 5 volts stabilizer, so that the whole circuit is powered from 5 volts. Okay, so now let's switch on the power and see what happens. Okay, as you can see, the diode was switched on. So now let's try to make some motion and check if it will be detected. What's important, I have the impression that this sensor needs about a minute to to start up. Yeah, and this is fact. I was able to read in a data sheet that such phenomenon really occurs. So now let's give it one moment. Yeah, okay, I think already now works perfectly. Yeah, exactly. Let's see. I shake my hand. It occurs the movement. Yeah, cool. Okay, and now I will quickly show you how the whole system can work without cooperation with microcontroller. For this purpose, it is enough to connect the signal wire from the sensor, so the yellow one, directly to the LED diode, of course remembering that the output current is maximum 10 milliamperes. So give me a moment, I'll rewire it, and I'll show you the results. Okay, and here you are, voila. As you can see, everything works just perfectly. Yeah, but the name of the channel really corresponds to reality. Let's do something that will allow you to make usage of the sensor, and by the way, you will be able to boast about something useful that will make your home become in some way intelligent. I will prepare everything necessary and invite you to the last part of the film. And here we are. I present to you a fully functional motion detection system and an illuminating LED strip. Because it's no longer a single diode, but a long strip, which is powered by 12 volts, and the power consumption declared in datasheet is 14.4 watts. So in this case, you need to make some modifications. From the programming side, everything looks the same. So our sensor is connected up to the one of microcontroller pins that detect the state of sensor, and second pin, here, and the second pin, this one is declared as output, yeah, but the LED with the resistor is no longer connected to it, but something else. What exactly? You can answer this question yourself if you answer on the other question. Which electronic element you need to use it both as a switch and which allows to handle such high power? The answer is very simple, and this is transistor. We have enormous choice of them. However, I will opt for the N-type MOSFET. Transistors are electronic components with powerful capabilities. Yeah, of course, not without disadvantages, but despite of them, they are very grateful. Let's briefly discuss the circuit. We have our motion sensor, Atmega 8 microcontroller, and MOSFET transistor together with two resistors. First one, and here is second one. It controls the activation and deactivation of previously mentioned LED strip, which is powered from a 12 volts power supply adapter adapted to work with high currents. Maybe I even show you this adapter. As you can see, it's a normal adapter, 12 volts maximum output current, 5 amperes, two output pins, plus and minus, three input pins, connectors. Two are obligatory. You must connect the phase wire, which is brown and brown color, and neutral, which is blue. Optional, you can connect protective conductor, which is, as I could remember, yellow-green wire. Okay, so now let's back to our circuit. Okay, seems good. Okay. So, as I told, the adapter has two pins, plus and minus. So the minus of this adapter, which is this brown wire, should be connected to a common ground of all circuits. So in this case, common ground, with stabilizer, microcontroller, transistor, what else? A motion sensor, and power supply of this circuit, excluding LED strip, because LED strip has another power supply, as we previously told, 12 volts adapter. The plus of adapter should be connected with plus of LED strip and the minus of LED strip should be connected up to drain of transistor. Yes, source of transistor, of course, should be connected up to the ground, and gate through the resistor should be connected up to one of the pins of microcontroller. Yes, let's talk briefly about MOSFET transistors, especially about this one used in the project. MOSFET transistors consist of gate, source, drain, and ground. The transistor will turn on when we apply when we apply the appropriate voltage called threshold voltage between gate. So I show it, the example of this transistor between gate and source. Then the so-called channel is created, and current can flows through this channel through the transistor. And of course, if we want to be more accurate, then we have to tell that, for example, the current flows through the transistor all the time, but it is negligibly small. I mean the current, of course. Yeah, I used the transistor IRLZ 44, yes, 44, and I used it for three reasons. First of all, very low drain source resistance. Secondly, the possibility of passing, operating with large currents. And thirdly, what's very important is, thirdly, the certainty that the transistor will open fully, which, as I said, is very important, especially if someone planned to operate on the 3.3 volts or voltage logic. Because this transistor has a very low threshold voltage. For example, in contrast to popular transistors such as, I don't know, for example, boot 11A. So you connect, as I previously said, the gate, the source of our transistor to a common ground, and the gate of our transistor to a microcontroller. To a microcontroller pin, which previously controlled the single LED diode. In addition, I advise you to connect, as I previously mentioned, two resistors. The first between microcontroller pin and transistor's gate. I use the value of 1 kilo ohm. And the second between the gate of the transistor and the common ground of whole circuit, or up to source, because as you know the source is connected also up to the ground. I used a value of 100,000 kilo ohms. It's recommended to use the values in range between 47 kilo ohms and 100,000 kilo ohms. And this resistor is also called pull-up resistor for P-type transistors and pull-down for N-type transistors. So why do we need this resistor if MOSFET transistor is, as we know, voltage controlled? I'm in a hurry to answer. As you probably know, the transistor is stuck, is not operatable when the gate and source have the same potential. So gate and source have the same potential. Sorry, I forgot the word. So if there's no signal on the control inputs, so in other words, it means that the high impedance is set, the pull up or pull down resistors set the same voltage level at the gate as on the source of a given transistor. So in the case of our transistor N-type MOSFET, this is 0 volts. So in other words, this ensures that the transistor is fully functional and operational. Yeah, okay, I think I've been talking for too long. This is not episode for MOSFET transistors, so let's get back to the most important thing. Yeah, because everything has been explained, then I invite you to the presentation of the circuit. I only switch on the power and come back in a minute. Okay, everything is already prepared. Then let's start the presentation. Okay, and I think that's all for today. As you can see, we've built a system that you can easily build on your own, and it can easily be used at home. It is simple to build, cheap, and has potential for development. You can add, for example, a photoresistor that will allow you to turn on the LED strip only if it is dark enough, or a button that will allow you to manually choose the option if you want the LED strip to switch on automatically, when motion is detected, or you want to switch them on yourself using the second button. Thank you very much for watching this video. I invite you to watch the other movies and invite you to the next ones, of course. In the description, you have the PCB board diagrams used in today's episode and a simple code to load into the memory of the microcontroller. See you next time. Bye.